Lecture 33, File System Implementation. Okay, so I said in a previous topic that we were going to discuss how a file is stored on disk. Unfortunately, we're not quite ready for the low level, all right, here's where like sectors correspond to the file kind of detail. We have to talk about something else first. You see, earlier on, we talked about the file system interface, and the file system interface was good. It's an important topic. We needed that, but we have to learn a little bit more about how it lives up to the actual implementation before we can think about the messy business of where to put file contents on disk. So the implementation is complicated, and to keep the size of the problem manageable, we're going to just talk about storing files on hard drives. As we've discussed in the previous topic, hard drives are sufficiently large and sufficiently cheap to store the data that we want to store. We can access an arbitrary part of the disk, and we can also access the same part of the hard drive an arbitrary number of times. They don't really wear out. Hard drives do have a limited lifetime. Nothing is forever, but for practical purposes, they are immortal, so to speak, as far as we're concerned. Recall also the disks operate on blocks, which is their physical representation, and a file comprises some number of blocks and some number of sectors. Now, we'll take a look at the file system design. As we start off, we're at a high level inside the operating system, and as we move our way down, we end up at lower and lower levels, closer towards the hardware, and having accordingly less and less abstraction. So, up at the top, we have the file system. And the file system, as we know it, is exactly what we saw earlier, the user-facing side of things. Now, it's convenient for the user to have this file system. It's convenient for application programmers. The interesting part is the stuff below that, which is how do we deliver on the things where we say, okay, we want to make a file. Well, let's make it, right? Where does it go? How do we make it? And where does it appear? And then below that, there is the I/O control level. And at the I/O control level, we're dealing with device drivers and interrupt handlers, and this is what happens when we are transferring data around from one place to another. And the inputs at I/O control level are somewhat high-level commands. It is something that looks like read block 1234, and the output is hardware-specific instructions to the hardware controller. So I want to do a read in my program. When I do so, I use the read system call. It goes to the operating system. The operating system sends this to I/O control, and it says, hey, the user program here wants to read block 1234 into memory. And then I/O control is responsible for turning that into something that the I/O controller, like the disk controller in this case, can understand. And usually that's writing bit patterns to the I/O controller memory to actually issue it the order that we are looking for. Then there is the basic file system. I hate the name. I think there's too much possibility of confusion here, but that's what it's called. This is the level at which we start to deal with the physical blocks on the disk. And a physical block is identified by how you get there. So we would say it's on drive 0, cylinder 12, track 7, sector 1, just to give an example. This layer is also responsible for buffers and caches that are used to hold various commonly accessed regions, like a temporary directory. Caching and buffering can appear in hard drives as well, not just in the operating system, but like on the board that controls the hard drive. This does mean that there's potential performance improvements traded off against the risk that some data gets lost if power is suddenly cut. If something has been put down as a write and it's been handed over to the hard drive, the operating system thinks it's done. It's not really and truly done until it's written in the magnetic disk. So there is a possibility of some data loss as a result of something like this because, caching is nice, but comes with this drawback. And then there is the file organization module, and this is a mapper between logical and physical blocks. So it takes a logical block address and turns it into the physical one, and also keeps track of where is free space on the disk. And then finally we have the logical file system, and this last level is for managing your metadata. It has the file system structure, directory structure, and maintenance information for all of that. File data is maintained in a file control block, sometimes abbreviated FCB, and the Unix term for this is an inode. We're going to talk about an inode soon, but it's the place where file information is stored, ownership permissions, but also the location of the file contents. So yeah, we'll talk about that in more detail in a bit. Now, all that's kind of abstract. We'll also talk about disk organization more generally. And there are a million different file systems. There's the UFS, the Unix file system, HFS Plus, which was used in Mac OS before the newer APFS replaced it. ZFS, NTFS, EXT3, FAT32, all of them. They're all different in various ways, and if we had the time, we could discuss the pros and cons of each of them, but like really, it's not so important that we should go out of our way to discuss that. It is noteworthy. There are important and interesting design decisions that go into each of those, but it's just not something that we're going to have time for in our discussion here. Whatever file system we have, there are some things that are in common that are worth discussing, and a file system has to keep track of the total number of blocks, how much storage is it managing, the number and the location of the free blocks, so how much of the space is available and also where is the available space, but also any files that are in it, right? We are, in fact, entrusting the file system to manage our files, and so it has to do that, and we have to store and retrieve them. And be able to use them again if we want. Now, on at least one disk somewhere in your system, there is some information about booting up the operating system. This is sometimes called the boot sector or something like that. And in a system that has more than one disk, it's not necessarily the case that the operating system is on every disk. In fact, it's probably only on one of them. But we need some information for where it is and how do we start it. And so to make that work, typically the first block of a disk is going to be the loader information to start the operating system. So when the power button is pressed on the case, turn the computer on, the BIOS or firmware starts up, and it transfers control to whatever is found at the first block on whatever the designated boot drive is. If you go messing around in the BIOS, you can probably see that you can select which is the boot order for things, and it will try to transfer control to whatever is found in the first block. Hopefully that's your bootloader, or at the very least, if you have a dual boot system because you have Windows and Linux installed or something, it gives you the option, and it says, what system would you like to start? Now, disks can be split, logically, into several different areas, which are referred to as partitions. And accordingly, you need then a partition table, and this is sometimes called a super block or a master file table, that gives kind of an overview of where the partitions are. And in the Windows world, we often see that like one whole disk is a logical partition, so like C drive, for example, might take up your whole primary disk, if that's what you're interested in. Here I've got a screenshot of the Apple disk utility, in which the disk is logically divided into different areas. So there's like Macintosh HD, that's your normal like file storage, and it represents this amount. You have High Sierra listed on there, I guess, because this is a dual boot setup of some sort. There's some other partitions, Sierra for like, yet another version of the operating system if you wanted to run all of those concurrently. And kernel dump storage does appear, but it's so small you can't actually see it at this level. So in this case, we have several different logical divisions of the same drive, right? It's one physical SSD, but it has different logical divisions on it. Now, it doesn't have to follow this rule. You can have like one whole disk is consumed with one partition. If I look at the backup drive that I have that I use for Time Machine in my laptop, the whole disk is given over to the one partition, and that's used to store data. Similarly, you can also have partitions that cover more than one disk. If you have a server where the disks are stored in some sort of RAID array, redundant array of independent disks, you can see that you could, if you wanted, make one partition that spans all disks. Now, in Linux, we often see also the disk is divided up to have partitions for different things. Temporary and swap partition will be different size than the home directories, and the boot partition is small. All these things are just organizations, logical choices about how to manage the data of the system. There's no reason why you have to follow a specific scheme. You just choose kind of what makes sense, right? Now, there are several structures of any file system that is loaded, we usually say mounted, that are likely to be in memory for performance reasons. So there's the mount table. This is the information about each mounted volume, disk, or partition. And that's just a way of saying these are the file systems that are currently set up, available, connected. When you have your backup drive connected, right, it's going to be mounted. That is, the operating system has said, all right, I'm connecting to it, I am communicating with it, so then you can interact with it. Number 2 in the list, there is a cache. Almost inevitably, there will be something in the cache because it's directory information for recently accessed directories, and probably we've at least recently looked at something, so that appears in the cache to make it easy to find things that we have recently looked at again. The global open file table, we talked about it in a previous topic, but effectively it is the file control block for each file that is currently open in some process or another. Now, it could be multiple if we have sharing of some sort, but this file control block has to be somewhere, so it's going to be in memory. And then we have the process open file table, and this is the per process individual file tables, so references into the global open file table, but organized by which process currently has it open. I think at this point we should be at least somewhat familiar with the process open file table. We talked about it on a couple of occasions. And then we have buffers. And buffers are places where data is read from or written to when we're doing a disk operation, right? We read data into memory, for example, but it doesn't necessarily go to its final destination immediately. What sometimes we'll want to do is read the data into a buffer until we have enough of the data and then go from there. Similarly, with writing data, it's sometimes more important to do it with buffering, where we are just waiting until we have a useful chunk of data to actually send to the block-oriented device. Now, creating a new file is a job of the logical file system, and that requires allocation of a new file control block or reuse of an existing free one. And a file control block, in general, contains stuff that looks like this, and we'll talk about the actual Unix implementation a little bit later on, but it looks something like this. There's permissions, there's dates that reflect when the file was last read, when it was last written, when it was last accessed, when it was created, who the file owner is, what group it belongs to. For systems that use access control lists, they get stored here as well. File size, how big of a file is it, and then the data blocks or pointers to the file data blocks, so the actual content of the file, if you will. Now, if we want to actually make use of a file in a user program, we use the open system call. Right? Open is used to say, hello, I would like to open this file, please, and we're also going to take a look at the permissions and verify, okay, you wanted to open it for writing, you have permission to write it, yes, okay. Or it's not open in another program exclusively, which would prevent us from opening it for writing. So that kind of thing is checked by the operating system. And open, as we know, operates on names like user-friendly names, where I say, I'm going to open example.txt, and that is something that I can understand as a human. The file system has to check the global open file table to see if the file is already open. If the answer to that is yes, then we have to check and see if it's open for exclusive access. Is the access that we've asked for compatible with whatever has been already registered in the system. So if it's been open for non-exclusive read access and we also want to do the same thing, great, sure, fill your boots. But otherwise we might reject that request. If it's non-exclusive access and this is allowed, we don't have to retrieve the file. We just add another reference in the process open file table. We say, aha, this file that was open for reading by process A is now also open for reading by process B. And we're happy with that because it's easy. We don't have to do any extra work. If the file is not already open, then the file control block corresponding to that file does need to get retrieved. We do have to get it from somewhere, and that means we have to fetch it from disk. And when we do that, we put the file control block in the global open file table, and we add the appropriate reference in the process open file table. Which makes sense, right? If we need to put it there, we put it there, and when we do, we reference it from the process table. And the process open table can also contain some additional information to help the user of that file keep track of what we're doing and where. Right? This contains, say, the read and write pointers, which you can move around with seek if you need. And although the open file is returned by open as a file descriptor in Unix, it's called a file handle in Windows. File handles are not the same as file descriptors, but the concept is the same. We have some sort of reference to a file. And as you know, we deal with a file descriptor, and so when we read from a file descriptor. When we write to a file descriptor. All of those things operate on this basis. And as I've mentioned previously, there's this idea of if we look at file descriptors and we just print them out as integers, we say, oh, and why is it 3? The answer is because that's the index in the process open file table, and that's the basis on which the system operates. So that's kind of neat. And the opposite operation to opening a file, obviously, is to close it. And when a process closes a file, an entry from the open file table can be removed. If this is the last reference to an open file that a particular process has, the file can be removed from the global open table, i.e. if it's not open in anything anymore. It is noteworthy in this regard that in a Unix-like operating system, if you delete a file and it's still open somewhere, the file doesn't actually get deleted until the last reference to it is closed. That does suggest that on closing the file that's open here, there is some extra work that's done to make a determination about, well, if the file was deleted while we were doing this, then it's time to send it to the trash can or just unlink it entirely. Another thing that's also kind of noteworthy on this is there is a limit to how many files that you can have open. I've done an example in which we run into trouble when we open 1,024 files or something in total, at least by default on a Unix system. And why is that? Well, because that's the size of the array in the open files table as far as a process is concerned. Another thing that we could look for is that metadata is updated when a file is closed, right? The last time it was accessed will be updated when we access it now, right? We've decided we're closing the file, and so that's the end time of our access to it, so it makes sense to update it at that point. That actually takes us to a small digression about metadata. And I want to give an example from Mac OS, and it's the Spotlight system-wide desktop search. There's a little magnifying glass icon in your taskbar. This kind of thing is used to find anything. It'll find emails, it'll find calendar appointments, it'll find files that you're looking for, and it will find file content. Right? If I'm searching for which of the lectures references Sherlock, right? If I search using the Spotlight search, because it indexes the content, it will actually tell me, aha, it's in lecture X and lecture Y and lecture Z. And it was really a revelation compared to previous search options that were slow. It really didn't contain the file content. The icon that you see there is an application called Sherlock, and it was a third-party app that was used for searching, and Sherlock has become kind of a verb in macOS user circles. To say your app got Sherlocked is like Apple releases in a future version of their operating system their own implementation of a tool, probably a paid tool, that your company made, and it renders your tool irrelevant. Right? Who's going to buy a license for your software for $27 US per year when it's included in macOS for free? And so if that happens, it's called getting Sherlocked. Now, with that said, Spotlight runs queries relatively quickly over the metadata of your system. It examines each file on creation and on modification, and it updates the metadata, thus allowing for relatively quick searches because you just have to search the index to find the stuff that you need. Now, it's not magic, right? This is a specific case of preparing the data in advance. Like, extra work is done by the CPU when a file is updated. When you open a document and you write a bunch of text into it, and when you save it, extra work is done at that point to scan over the file and look for things and index it accordingly to try to make it possible to find it later, right? It's doing work in advance to prepare for a future request. If you needed to export accounting data to Excel, one is to examine the data and create it at the time when the user requests it. So when you request the report, it scans all the relevant files and it compiles the report and it prints it out. Or alternatively, you could actually just have these things maintained separately, and so when the Excel report is asked for, you don't have to do the work of compiling the overall results. You just take the data and you export it. Right? This is an option. It's a design decision. It depends on how expensive it is to compile the report and how often the data changes and things like that. But Spotlight is actually a specific example of doing something in advance to prepare for a potential request that could come, right? I write some stuff in a document. I may never search for the contents of that document ever again. This is just an essay for a course, and I submit it, and I never need it again. That would be fine, right? Do we do some unnecessary work? Maybe. But that actually takes us to this idea of, well, part of the difficulty with maintaining metadata is how often do we update it? Right? The more often we update it, the more work is done to keep it up to date. Right? We have to analyze the document every single time and add and remove things from the contents of the index every time we find that the content has changed. That could be a lot of work. The longer the time between metadata updates, the higher the chance there will be a user request that gets back some out-of-date data. That's not always a problem. Right? For some things, I don't need perfect information. I just need an estimate. When we're looking at enrollment in a course, during the add drop period, I might be looking at the enrollment of the course, and I might only have the information that's up to date as of yesterday. But that's fine, right? The amount that it has changed in the last 1 day is probably fairly small. It's not going to be dramatic. Right? It's not going to be that yesterday there were 3 students in the course and tomorrow there are 300. It's much more likely it's going to be yesterday there were 127 students in the course and now there are 129 because 2 people added the course and that's fine. Having data in that case that's a little bit out of date is not a problem because there's sort of no impact. But for some things, you really do need the most up-to-date data. If I'm looking at my bank account balance, I really do want it to be up-to-date because that is important to answering important questions like, what can I have for lunch today? Or will I be able to pay my bills at the end of the month? So in that case, more time and more processing power should be spent updating the metadata so that this is correct after every transaction and not just updated at the end of the day. And so this diagram that we're showing here gives us kind of a overview quickly of opening and reading from a file. So if we open a file, right? In kernel memory, we're going to search around a bit to see if we have the file. If we don't, we have to go to secondary storage, that's disk, and we'll load the file control block into the kernel memory. And then when we want to do a read, we specify as the caller of the read that we're interested in the file descriptor that references an entry in the per process open file table, which itself references an entry in the open system file table. And the file control block is what's in there, and it contains the information that tells us where the data blocks of the actual file are. So you can see, I think, some of the distinction between these different levels. Now, there are a lot of different file systems out there, as I've mentioned, ext3, ZFS. We don't actually care about the details too much right now, but they can coexist in a system, right? You can have a disk that's formatted in one file system and another disk that's formatted in another one, and that's the case, for example, if I look at my laptop, the main built-in drive is formatted APFS, the new Apple file system, and the Time Machine backup drive is formatted HFS Plus, which is the previous commonly used Apple file system, and they're two different disks, so it's okay to have them be different in terms of how they're formatted. From the user's perspective, though, there kind of isn't any difference, right? Why does it matter? What if I say copy a file from one to the other, move this file from the main disk to the backup drive? Who cares what the underlying file systems are? And to make things a little bit easier for the system, there can be an additional layer of abstraction called the virtual file system. And the virtual file system is, first of all, to separate the file system operations, reading, writing, opening, closing files from the actual implementation. And then the second is to provide a mechanism for representing a file uniquely throughout a network. So the first part is beneficial because operations can be done with whatever file system is underlying it. The second part is more interesting, though, right? If we are sharing files, from servers across the network, that kind of thing, we might need a way to specify unique files. Which one are we referring to? There's probably lots of files called example.txt. And the final representation in the virtual file system is a structure called a vnode, which is kind of like the Unix inode, but inodes are only unique in the same file system. So you can have two inodes that are identical on two different disks, whereas the vnode is supposed to be a globally unique identifier here. Now, all that really turns into is it looks something like this diagram here. We have a file system interface, which then has an interface to the virtual file system, and the virtual file system is responsible for figuring out which of the underlying actual file systems is responsible for containing that data, and it may be a local disk or it could be over the network because we do have the ability to connect to remote drives. You probably do it with the university storage that we give you. So that kind of makes sense. And the VFS architecture in Linux has four main things. It has an inode, which represents an individual file, a file, which represents a file that is open right now, a superblock, which refers to a file system, and then a dentry for directory entry. For each of those, there's a set of operations defined, and we're not going to get too bogged down in the details here, but for a file, we have read, write, open, flush, release, those kinds of things, without having to care about the specific implementation, because the underlying file system will have a different way of flushing data out to make sure that everything in the cache is written out. There's going to be different implementations from different file systems, so it's nice if we don't have to concern ourselves with the specifics. We'll also talk about directory implementation. This table, which please do not attempt to memorize this is kind of ridiculous, just gives you an idea of the different attributes that could hypothetically appear on a directory. There's a name, type, organization, volume, access control information, usage information, all of this. all of this is to say it's just a little bit crazy, right? There is a choice to be made in how directories are implemented. You could choose like a list versus a hash table. You don't have to choose one or the other. There's lots of ways we could do it in different file systems. There's no guarantee that necessarily one implementation is the best. The important thing to note, more or less, is that the directory is a way of organizing files, right? And if you use Vim to like look at a file directory in Unix, you'll just see it contains some information like a list of files. That's enough for our purposes. When we create a new file, we need to search the directory to see if there is a matching file name. If the answer is yes, then that's an error because the file already exists, so we can't create a new one with the exact same name. If not, insert a new entry in that list. Deletion is also simple. Search the list for a matching file and remove it. If it's the last reference to a file, it's not used anywhere, it's not open anywhere, then we can free up the space. But of course, given a sufficiently large file system and given enough files, searching it linearly takes a long time, right? And it has linear characteristics, so that makes sense. A hash table is also potentially okay. The hash is computed based on the file name, so there has to be a strategy for dealing with hash collisions, where you can use a perfect hashing algorithm, but we'll come up with something, right? Neither of those is great, though, because what we actually want is a more complex structure. What we need is a tree. Okay, you learned about trees, I'm certain, in a data structures and algorithms course, right? Surely we don't have to go over trees again. Now, an AVL tree could be good because it is a way of storing data in an orderly format. But what I'm actually going to argue is that it's not optimal for our situation because it doesn't match the block system of a hard drive very well. If we want to use the hard drive efficiently, right, what we don't want is to retrieve a node, and a node is, let's just pick a number and say it's like 64 bits, or even 64 bytes, and that's not helpful, right? Like just retrieving one of those and then having to do another disk seek and retrieve another one is not efficient, because when we do a load from a hard drive, we load a whole block. If a block is 4 kilobytes, we should be thinking about how many nodes of the tree can we fit into that 4 kilobyte block. So that's our goal. Each node should occupy one block. Accordingly, each node can contain a lot of information. And file and directory information should be kept linearly ordered to make it easier to iterate over it and find what we need. But a block doesn't have to be full. Right? We can have a partially full block. In the ideal situation, of course, it is completely full, but the file might not be that big. And if that's the case, well, then it isn't. If a leaf node gets full, we can split it into 2 half-full blocks, which then sort of allows more space to put more stuff, which, again, is going to make it relatively efficient, since each node is at least half full. And keeping the tree balanced is also important because it will help us, no matter how big the file is. If the tree is balanced, then finding an arbitrary part of the file takes about the same amount of time no matter where it is in the file. So B-tree is really good for this kind of structure. And a B-tree formally has the following characteristics. Some of it is very basic, like down to like what even is the definition of a tree, but that's fine. I prefer we are complete as opposed to overlooking something that is important. So number 1, the tree is made up of nodes and leaves. The distinction between a node and a leaf is a node has children and leaf has no children. Each node contains at least one key identifying a file record, and more than one pointer to child nodes or child leaves. So the tree can have like multi-levels, but every node has to have a pointer to something. Each node has a maximum number of keys, and the keys in a node are stored in a non-decreasing order. Every node has at most 2d minus 1 keys and 2D children. So if we look at the properties of the B tree, if it has degree D, then there are 2D pointers in a node. Every node other than the root has at least D-1 keys and D pointers, such that each internal node except the root is at least half full and has at least D children. All leaves appear on the same level. That's part of what makes the access equal in terms of time, no matter where stuff is. And a non-leaf node with K pointers contains K-1 keys. Okay, it's a lot of rules, but it does make it fairly easy to find something that we are looking for. So we start at the root node. Imagine that we are looking for block 21. If that's the case, great. We start at the root node, and if the key 21 is in the current node, we're finished. We get the pointer to the data, and we don't have to do anything else because we already found the data that we're looking for. Perfect. What could be easier than that? If the key is less than the smallest key in this node, well, then we follow the leftmost pointer, takes us to another location, and we go to step 2, carry on. If the key is greater than the largest key in this node, we follow the rightmost pointer and go to step 2. If it's between the value of 2 adjacent keys, we follow the pointer in between them, and again, go to step 2. Insertion is much more complicated, and this slide definitely needed breaking up into more than one slide because it's way too much text. If we're going to do this, we search the tree for the key, and if it's not found, then we at least end up looking for the block where it would be if it were there, right? If we find a specific number, it's already in there, so inserting doesn't make sense. But even if we don't find it, the process of searching for us takes us to the location where, if, hypothetically, it were in the tree, this is where it would be. So that saves us from having to do the search and the insert a second time. Because if we know where it should be, if it's not there, well, it's pretty easy to decide to put it there. If this node is not full, insert the key into this node in the proper sequence. So that's the easy case. If the node is not full and we're in the right place, we just put it in there. In the harder case, we have to split the node. And we split the node around the median key into 2 new nodes, each with half of them. And we take what was in the middle and we move it up to a higher level. If the new node is less than the median, insert it in the left-hand new node. If it's larger, then put it in the right. If the node that we've just promoted, moved up to the parent, is inserted in there, great. If that's not full, there's no problem. If adding it didn't cause a problem, we're okay. It is possible, however, that we have to repeat the splitting procedure in the parent node as well, in which case, well, we go all the way up to the root node if necessary, and if the root node is full, then potentially the height of the tree increases by 1. That sounds like a lot. The algorithm is okay to implement based on this description, but it's probably not super easy to understand. It makes more sense when we look at some examples. So let's imagine here that we want to insert some keys, right? If we're going to search, that's easy as well. And because searching is a necessary part of inserting, then I'll not do searching separately. So let's say we wanted to insert 3 into this B tree. Right, we start out at the root node, and the root node contains 23, 51, 61, 71, so 3 is definitely less than the smallest number. In that case, we follow the leftmost pointer, and we end up at the node that currently contains only 2 and 10. When that happens, we insert it in its correct place there. If we were looking for it, we see it's not there. And if we're inserting it, well, we're still at the correct place. And what we'll do is we'll insert the 3 in between 2 and 10. Okay, that makes sense. And that was an easy case, so we're finished. It gets more complicated if we are inserting something that is going to result in splitting a node. So the example here, key of 90 is inserted, takes place as B in this diagram, and that's also a simple case because we're just inserting it into the rightmost node, so there's nothing to do there to split it. But if we insert 45, If we look at the pointers, it goes between 23 and 51, so it would go to the second node from the left, according to our diagram, and that node is already full, right? It contains 5 pointers already, so there's nothing that we can add here. So we do a split. And to do the split, we look at the median key. In this case, the median is 39. So 39 is promoted to its parent. That happens to be the root node. And then things that are less than 39, so 30 and 32, go in the left child of 39. And things that are greater than that, 43, 44, 45, go in the key to the right of 39. Okay, so that ends up splitting a node into 2 parts. Each is close to half full, and it promotes one of the nodes to the root, as we would expect. Okay, now that's not the hardest possible case, because it's also possible that we have kind of a cascade, right? If we do an insert of the key 84 into this, so given C, we're going to insert 84, it's going to result in promotion of a new level of the tree, right? Because we want to insert 84 here in the rightmost column. It goes between 73 and 85, but we have to split that node. When we do that, it would promote 88 up to the root node. The problem is the root node is already full. So we repeat the split procedure there, just as if we were inserting 88 here. And what we end up with is 51 is the median key. So 23 and 39 are the nodes that are to the left here. So that's created. And then 61, 71, to which we insert the 88 when it is added. So that's fine, and in total we have now split the node into 2 parts, promoted a key to the root node. The root node itself needed to be split and promoted, so now the depth of our tree has increased. Okay, that's kind of like a long explanation, and hopefully now with a couple of worked examples about how the B tree works, it makes it a lot easier to understand the algorithm that we saw on the previous slides. Given this, we're now actually ready to look at how files are stored on disk. I know I've been saying that, and I know we took sort of another digression, and sorry that I tricked you in a way into going down this route first. But don't worry, we will definitely be talking about how files are stored on disk next to close out our discussion of file systems.